Wasabi, you guys. Welcome to Integration Beat Training for Advanced. This is part 16.2, and in this section we're going to deal with trickier limit integrals. So let's get started. So we have this awkward looking integral. What do we do? And it doesn't look like we can just simply do, I don't know, like L'Hopital's, because it looks off, right? So what we can do is let u equal n over 1 of x. So I just want to force u substitution to see where this can lead to. And in this case, if we let ln of u, this equals to 1 over x ln of n. Okay? And so what we have is x is equal to the ln of n over ln of u. Okay? And then dx is going to equal to negative u ln of u squared. This is going to be ln of n du. Okay? So now when we go ahead and do our u substitution, so we do a forced u sub, and here we see if we plug in n, here actually, if we plug in n, we get n, 1 over n. We're going to use the negative to change our bounds. So 1 is just n, looks right. And now we have ln of n over, well, our u was here, but we have this u, so it gets cancels out, so we're left with ln square of u du. Okay, now what? What on earth do we do now? So, of course, if we, let's see, let's rearrange this a little bit. Okay, let's add an ln of n. Okay, this is equal n ln of n, like that. And we have our n, 1 over n here, du ln square of u. Okay, so clearly this is not, well, we don't know what this is actually. We could go ahead and write it in a different perspective, right? Is this infinity? Well, I mean, ln of n over n, if we do L'Hopital's rule, this is going to be 1 over n. So this is e to the 0, so this is going to equal to 1. Okay, so we have 1 to infinity of du over ln square of u. Is this equal to infinity? The answer is yes. At this interval, from 1 to infinity, right? Whatever, what, ln of 1, let's see, 0. Well, I don't know. It's something like this. Something like this, I don't know. But I could be wrong. But whatever the graph is, the area under the curve is going to be infinity, because at this interval, this function is increasing. So, therefore, for this integral is going to infinity, and this integral here is also going to infinity because n is bigger than ln of n. So, with that in mind, we can use L'Hopital's rule. So, let's go ahead and take the limit. Oh god, I can already, oh god. This is horrible. I can already see. This is god awful. Let's start. This is quotient rule. This is ln minus 1 ln square. Okay, but here, like I said, it's, well, here we have 1 over ln square of n. Okay, but then minus, and then we have this here, which is, oh god. we have ln of n over 1 over n. So that's like what? ln square n square when we take it out of the ln. And then the derivative of n to the power of 1 over n is, well, I know it's going to be this, but then it has the other stuff, which is, oh, I think it's just quotient rule. Yeah, it's just quotient rule. Like that. It's just quotient rule. Because I'm doing loophole log in my head. But yeah, that's the derivative of this. Okay, so ln square is getting cancelled out. Let me tell you that. And then n square here. This n square is also cancelling out. Okay. Okay. So our limit is now 1 minus n over, n to the power of 1 over n. 1 minus ln of n. And then ln of n minus 1. Okay. So this is what we have. And then, like I said, like we just find the limit from this. We just noticed that this is equal to 1. And so, from this, let's see, if we let infinity, oh, well, if we focused on this term, that's going to be 0. So ln of infinity, 1 over infinity is 0. And so this cancels out. And so, wow. So we really did have this. And this does equal to 1. So, our answer to this integral, this very sneaky integral, is equal to 1. Okay? A lot of manipulation. The hardest part is, when in doubt, force u sub everything. Right? If there's an awkward, let u equal this whole thing and try to change it into a different integral, pretty much, and see if there is something that we can do from here. And turns out we could. And then another tricky part is understanding that this integral goes to infinity and being able to use L'Hopital. Okay, so a very, very tricky integral here. Okay, very tricky. All right, let's do another tricky one. So we have like an integral inside of an integral. Very terrifying. I will be honest with you. So, how on earth do we do this? So notice that we have n here, we have n at the bottom here, and we have n here. So it seems like we might have to use L'Hopital's rule. So let's go ahead and do L'Hopital's rule. Okay. Let's actually put this inside of the integral from 1 to 2. And then the limit as n approaches to 0. First off, we can format this as from 0 to n. I'm sorry. etx dt minus n nx plus 1. Okay. And so when we do L'Hopital's rule, oh god, it's so this is what, minus 1, and then this is FTC, fundamental theorem of calculus, deriving an integral. So we have e to the nx minus n, minus 1, that n becomes 1. And then after that we have this here, this is power rule. So this is just power rule, x plus 1 of n to the power of x. Okay. For some reason I was thinking about, I don't know, I accidentally derived x, but this is what it should be. Okay. So power rule, that n, this is power rule, do not derive x by accident. Okay. Alright, cool. So now what we have here, this is a lot much simpler to work with. So we have from 1 to 2, limit as n approaches to 0. Okay. Now we still have a little bit of issues here. We still have to do L'Hopital's. We just have to move the x plus 1 out of this mess. Let me just go ahead and do that right now. So now we have the limit n approaches to 0 of nx e to the power of n to the power of x minus 1. Well, would you look at this? Didn't I showed you this limit before, right? Baby limits. We can use baby limits. E to the n minus 1 over n is equal to 1, right? This is the exact same format for n to the power of x. So, but you can be safe though. And the reason why it's a little iffy is because we do have x here, right? If we plug in n as approach to 0, right? 0 to the power of x or 0 to the power of x. I mean, I guess that still equals 0 because x is between 1 and 2. But if it was something else, I guess we just have to be more careful and actually just, you know, L'Hopital's rule. But I'm confident that this does satisfy the baby limit. So in that case, this whole limit is just going to equal to 1. So from 1 to 2, we simply have dx over 1 plus x. So our answer is ln of 3 over 2. Okay, but if you're unsure, you can go ahead and feel free to do L'Hopital's rule. It should come out the same exact. Now I'm looking at it, it should come out as 1. Yeah, because you get the derivative of nx, and you derive this, you get the same thing here, times the derivative of nx, so the derivatives cancels out each other. You're left off with e to the n to the x, plug in 0, and you're just, yeah, e to the 0 to the power of x. Depends on what interval. Yeah, it does depend on the interval. From 1 to 2, since x is between 1 and 2, this is going to equal to 0, so e to the 0 is 1, so the limit does equal to 1. So this is indeed our answer. Okay, very scary looking, I will say, like an integral inside of an integral. This will problem shock a lot of competitors, but take slow baby steps, and you'll get through it. Okay, we have this integral here. So baby limits, again, baby limits is very useful because this looks awkward, right? So the baby limit I'm going to use is sine of n over n, and because this is going by infinity, right, the limit of this is equal to 0, okay, by squeeze theorem technically. And so that's what I'm going to do here. However, I need the same thing from n over n, so that means that I need x over n at the bottom. So I do have an n, right? We have sine of x over n, and I do indeed have an n here. But I need an x, so I'm going to have x, so that means that I just divided x times x. And then I see e to the x here. I'll have that. And now if I plug in infinity and infinity here, I simply have 1 to infinity. This is just equal to what? Oh, I'm sorry. What we actually have is this. Then it's not 0. This is equal the same thing as this when you flip it. This is 1. Oh, even better. I was about to say this whole integral equals to 0 when there's 1 to infinity. I don't know about that. But okay, this makes more sense now. Yes, this limit equals to 1. Perfect. Now exactly what we have is just this integral here. Okay? It's not gamma because this is 1. So be very careful with that. So our answer, we'll just go ahead and do integration by parts, and then plug in 1 to from 1 to infinity, and your answer should, let's see, infinity is going to be 0, so that negative is going to cancel out, and so if we plug in 1, we will end up with an answer of 2 over e. Okay? So that's our answer. So this limit integral is equal to 2 over e. So baby limits, super helpful. Use baby limits. Okay? So we have this very intimidating looking limit integral here. So first of all, I like to combine this. You would say this is like what? Like an odd function, right? A lot of you guys would assume this is an odd function because of this x. However, this is an even function. Okay, this is even. Be very careful. Okay, this is even, and let me show you why. This limit, if you simplify this, this is 2n plus 2. 2n plus 2 over 2n plus 1. Okay? Meaning that this is x squared of n plus 1 over 2n plus 1. Okay? This is an even function. This is not odd. Be extremely careful. Okay? Now we can use symmetry. This is from 0 to infinity now. 1 times 2. Okay. And so now, if you plug in infinity, first off, we have, I like to use negative e to the negative nx so that it converges more. So from limit to infinity, we're going to go ahead and do, I'm just going to write it like this. So we're going to take a divide e to the nx out. So we're left with e to the x, while inside of this n root we have 1 plus e to the negative 2nx, right? And so now, if we plug in infinity, this is just 1, and then this is just what? 0, 1, 0 to 1, let's see, 0 to the power of 0. It's like limit n approaches to 0. N to the power of n, this is just also going to equal to 1. Okay? So this is also equal to 1 as you take the limit. So now our integral is simply this. It's a gamma function. This is the gamma you want. So now your answer is 2. Okay? Alright, a lot to take in, I will say. So it is a lot to take in, a lot of sneaky things that you have to be aware of, a lot of traps and dangers of limit integration. Okay? Again, this is just the basics. This is just a little territory of the first level of limit integrals, L'Hopital's, or just dealing with limits in general. But with integration, these are like traps that you have to be aware of and be careful with. Okay? So definitely rewatch this video and try the integrals on your own so that you become more comfortable with these limits. Okay? Alright. I hope this is very helpful. Thank you so much for watching, and I'll see you guys in the next part.